This is a lesson 11-1. We're going to take a look at limits as they go to infinity. Now when we have limits that go to infinity, we're going to have a few features that kind of interact with our graph, namely asymptotes. And these asymptotes actually have a major impact in how our function looks. Now if you remember, asymptotes are those imaginary lines that graph approach but will never ever reach in most cases. And so visually here we can take a look at asymptotes. This is a vertical asymptote and this is going to be a horizontal asymptote. Now the idea so far when we had limits is it would approach a certain number and we would be able to approach that number from two sides. So for example, if I approached 2 from the positive, so I'm approaching 2 from the positive, my graph is going down forever, and I would say that this equals negative infinity. And when I would approach 2 from the negative, so I'm approaching 2 from the negative, it looks like it's going up forever. And so I would be able to say that that's going to be positive infinity. So it's because it's approaching the highest possible value. But now things change just a little bit when I say x is going to infinity, or I could also say x is going to negative infinity of my function. Because notice, as x is getting really large, we can make an assumption about that value that my graph is approaching. And in this instance, my graph is going to be approaching that value of 1. Now, when we have these limits that approach infinity, it's very similar to end behavior. So reviewing the lessons in pre-calculus about end behavior, it might be helpful, especially when it comes to polynomial and rational functions, because you're going to see a lot of similarities between the two. Now here's a definition that we need to remember, and this is almost from the rational functions playbook when we're trying to find the horizontal asymptote. And so let's just say hypothetically I have this limit as x approaches infinity and I'm dividing my two functions. I'm going to say that n is the degree of this and m is going to be the degree of g of x. If the degree on top is larger than the bottom, then my limit's going to approach infinity or negative to infinity depending on how the direction that it's going to go, because negatives when it comes to these functions can't affect that. If my degree on the bottom is larger than the top, then my limit approaches 0. And then if the degrees are equal, then the limit is the ratio of the leading coefficients of my function. So let's apply this definition to a few examples. So it says evaluate the following limits. So because of this definition here, what I can do is I can actually kind of synthesize or simplify and look for patterns here. So I look at my n and m and notice that 5 is greater than 3, so therefore my limit is going to approach infinity. On this next one here, sometimes we can get fancy with square roots and how things are taken to a power. But just know, all we're looking at is just the highest power. So because this says the cube root, well, the cube root of 12, well, that's just x to the 4th. And then down here, the highest power is x to the 7th. Well, the degree in the denominator is larger, and so that means that my limit is going to approach 0. And then for this last one, I have to look at my leading coefficients. If you notice, here I have negative x to the 3rd, and here my n and m are equal to each other, and so it's actually going to approach negative 7. Now to conclude our lesson, it's just a helpful reminder to know that when you take a limit and you approach it to infinity, it's very similar to end behavior, especially when it comes to rational functions. And so taking a look at that definition or that pattern that we established here, if I do have that limit as x goes to infinity of f of x over g of x, I said n is the degree of the numerator and m is the degree of the denominator. When the degree on top is larger, it approaches infinity. Now, it could also be negative infinity based upon the circumstances, of positive, negatives. That always changes things. If the degree on the bottom is larger, it'll always approach 0. And if the degrees on top and bottom are the same, then the limit approaches the ratio of the leading coefficients. This does conclude our lesson. If you have any other comments, please leave them in the... This does conclude our lesson. If you do have any other questions, please leave them in the comments.